otherwise contributed to the conference. And it's good to have so many people, I think, that might not have otherwise been able to attend. So that's certainly one silver lining in the dark cloud that is the current travel situation for many people. So one way or another, whether you could have made it in person or not, glad to see everybody here. And again, we'll give it another minute or so and let Daniel take it away.
Can you all hear me fine? It's a very hot day in Pisa today.
Does that improve or degrade response time, the heat?
Yeah, it's I have a cooling system, so I put a stable frequency.
All right. And Stephen just showed up in time to give you a hard time. So here you are. Go ahead, Daniel. You're all yours.
Okay, here we go. So hello, humans. I'm Daniel. I work for Red Hat, and this is the work I did in collaboration with some folks at Scuola Superiore Sant'Anna here in Pisa and Universidade Federal de Santa Catarina in Brazil, right? And today we talk about, guess what, real time. And for those who attended the Plumbers last year, I would say that this is the episode 3 showing the math talk. And we'll talk more about this during the presentation, right? So, yeah, I'm from the real-time Linux community. And but sometimes we need to say real-time Linux, mainly when we are in front of academic people who have another or a different, let's say different, but yeah, a different point of view about real time. And, that's because on the real time Linux side of the fence, we took a more experimental approach, while in the math and the real time theory we have right also there. So they have a more analytical approach, right? For example, Linux was adapted to become a real-time operating system. The parameter RT is the de facto standard for it, and we have many people running this in production as a real-time operating system. And the main tool that we use to evaluate the parameter RT is actually the cyclic test that analyzes the kernel somehow like a closed box. And this brings some criticism to how Linux performs, because despite the fact that cyclic tests help a lot, it doesn't give a demonstration of worst case, which are common in the real-time literature, and does not demonstration and evidences that the worst case was found while running the system, right? You never know if you hit the max latency or not. On the other side of the fence, in the real-time theory, the studies are made on top of a very precise description of the system that tries to capture all the behaviors. They precisely define the worst case, and then they can say like more strong arguments about finding the worst case, right? Not just trying. But sometimes it's overly simplified, because to be able to do the math, they use models that are not necessarily connected to the things that we see on Linux, for example. They say that tosts are independent, that operations are atomic, and such simplifications make it sometimes hard to feed Linux and real-time theory in same room. But the point is that I like both. I like real-time Linux. I like the folks in the real-time Linux community, and I also like folks in the academic side. I have good friends on the both sides of the fence. And yeah, I'm trying to put them all together and make everybody happy. So, and this presentation actually is based on a paper published on the ECRTS. There are three main conferences on real-time theory, real-time systems, which are the RTSS, the ECRTS, and the RJS, and this was published on one of those conferences, the ECRTS. So, why this is the episode 3? Because 2 years ago we got the episode 1, in which I showed my idea that, okay, try and say that Linux works in real time is cheap, we need to show the math. And on that talk, I explained that I was trying to specify the behavior of the parameter RT using the automata theory, right? Trying to reduce the complexity of Linux using a model. And actually, that work is the base from this paper that I presented in this talk, right? So the approach here was, we analyzed that formal specification, we produced a scheduling latency bound explanation following the kind of the methodology commonly used in the real-time theory. And then we made some measurement and analysis to see, okay, how bad Linux is using those pessimism and those more rigid analysis. Okay. And okay, from that talk, I explained that I model Linux using a set of generators, which are where the independent behavior of the system. And then in the paper, in the approach to demystify the real-time Linux and latency, to reach the theorem, we translated those generators into a set of operations, right? On a natural language explanations of operations of Linux. And then we got specifications, and the specifications are the coordinated behavior of these generators. An example of a generator is, I can call the scheduler and return from the scheduler, and I can disable interrupts and enable interrupts. And a specification is like, I cannot call the scheduler with interrupts disabled. Right? And these are some kinds of rules of synchronism of Linux. And that we use this word, like we explain this as the rules of synchronization of the system. Okay, from that basic operations and the specifications, we define what could be the scheduling latency. Okay, we want to show the timing behavior of the scheduling latency. And we defined it as the longest time elapsed between the time A in which a thread, right? Here I say job, but it's a thread on Linux terminology, which a thread becomes ready and with the highest priority, right? Until the time in which this task starts to execute, right? And it's important to mention here that ready and with highest priority are two different actions, right? And I'll explain it better in the next slide. So, okay, I want to define this delay between the task being ready and with the highest priority up to the time in which it starts to run. And to break down a little bit more this problem, we separated two kinds of abstraction. We have the thread running, the current thread running, and this new highest priority thread who just arrived, right? And then we break down this delay into the delay caused by blocking and the delay caused by the interference. Blocking is a terminology used in the real-time theory for the case in which a lower priority task delays a highest priority one or a higher priority one. And interference means when we have a higher priority task interfering in a lower priority task. For the case of Linux, we use the blocking to define the delay of the lower priority thread, causing into this new highest priority one. And interference we use for the IRQs that happen during this time window. So, from the bound of the blocking and the bound of the interference, we started bounding the blocking time. Right? And to do this, we used the specification of the system used in the formal model. And we got an auxiliary image, which is a timeline, which is used in the real-time theory. And I'll explain it better. Right, so, okay, blocking the bound. When does the scheduling latency start, right? It's in the instant of time in which a thread becomes ready and with the highest priority. The event that better notifies that there is a new highest priority thread on Linux is the set need resched, right? And so we have the set need resched that works for all schedulers and all conditions. And this set need resched, it has two necessary conditions: preemption and IRQ should be disabled. So we bounded back the starting of the scheduling latency to the instant of time in which the preemption or IRQ became disabled. This is the furthest back that we could see. Then the end of the latency on the blocking is the time in which the scheduler returns and allows the execution of the new highest priority thread on code. We generalize this instant of time to the point in which the scheduler returns and the preemptions get enabled after scheduling. So it's important to note here that this implies that the context switch, we cross it by the context switch, and the context switch also implies doing the scheduler, so they are bidirectional. And it's important here for the demonstration that the context switch needs preemption disabled to sched and IRQs disabled, and we will reach it. So just recalling the scheduling latency, so for the thread arguments is in the first starts when we first see either IRQs or preemption being disabled and then causing need resched, and the time in which we have the highest priority thread already scheduled and the scheduler finish running, enable preemption, and then it's the on-thread code. So, and how do I bound these two events, right? Disabling preemption to cause the preemption IRQ to cause the need resched, and the return from the scheduler, enabling the preemption. There in the formal model, there was one specification that says that the set need resched is a sufficient condition for a context switch in of a new thread. Anytime I have set need resched, I will only return to the initial state after having a context switch in of another thread. There are just these two paths. Then here inside we have all the possible paths in the synchronization level, right? Preemption enable, preemption disable, calling scheduler. So in the synchronization level, we have all the possible paths that we can face here by the kernel. And from these paths, we distinguished 5 possible cases. So, and then we use the timeline to explain it here because it's easier. And that's normal, right? And when we are doing this argumentation on paper, we can use these auxiliary formats to help in the demonstration. So, think on this on that task running, right, on the CPU. This is the scheduler context, right? This is disabling preemption to call the scheduler runs. We have the context switch, and the scheduler returns, and we have another task running here. And here is the previous task that was working. We can have the arrival of the new highest priority thread in any time here. And from the specification, let me see if it's in the next slide as well. From the analysis of this path, we found the situation in which, let's go from the most optimistic to the most pessimistic. We could have a new highest priority thread being very lucky in the case in which the lower priority thread was calling the scheduler to suspend, to go to sleep, and it was already on the path to call the scheduler. So if my new task is lucky enough, it will arrive here while the scheduler is already running, right? Or there is a case that that doesn't actually exist in reality, but it would not break the model, in which the scheduler code would wake up a thread as well. So if the thread, the new highest priority thread, is lucky enough, we will have this case 1A and 1B covered here. It's 1A and 1B. The former thread was already calling the scheduler, and all the good conditions were there. Okay, good, lucky, but this doesn't always happen. There is one unlucky case in which, let's say we have a timer interrupt, and it would arrive right here when IRQs get disabled to cause the context switch, because IRQs disabled, the IRQ disabled has this necessary condition of having IRQs disabled, context switch. So if my timer arrives here, the IRQ will be disabled, and then it will only be served here. And then we will have to go this path again. And then we have this case here, right? This timeline here, the case 3. And we have the more common case, or the most unlucky case, in which the current thread was not wishing to go away. It was just running. It could have disabled preemption, or it could be running on user space. And then its code is running, and we have the preemption disabled either by the thread or as a side effect of the arrival of a new thread, or to cause the need reset, or to cause the need reset. And then we have all this delay, which are the cases 1A and 1B. And then in this timeline, we covered all the possible cases here. And this gives us the assurance that we're not forgetting any path. So, good. We demonstrated all the possible cases and showed that the latency will be bound by either this case here, like on this, or getting here. So for us to make a computation, okay, I have the behavior, how can I abstract these into mathematical variables that I can use on an equation, right? So we found that the most practical variables to explain this dynamics would be this. Sorry. We have this variable that accounts the preemption or interrupts disabled to postpone the scheduler, which is the classical case in which a thread is running, disable the preemption, do something, and enable the preemption, for example, but not call the scheduler. We have the time window in which the preemption are disabled to call the scheduler, because the scheduler is called with preemption disabled. We have this window here, which is after disabling interrupts during the scheduler to cause the context switch. And we have this transient state here that happens inside the preempt enable, or inside the return from my IRQ, which is I had the need reset. The system is enabling the preemption and IRQ because they are necessary conditions for need reset. And then when both are enabled, we check for need reset. If there is the need for reset, we call the scheduler. And we have this transient state in which the preemption and IRQ are enabled, but then we strictly connect with the next disable. Okay, returning to these variables to the timeline because it's easier here. So we have the sched tail latency, the preemption, the sched disabled to cause the scheduler. The preemption disabled to call the scheduler. Slow down. We have this window here. We have the window of preemption and IRQ disabled to postpone the scheduler, and this tiny boy here, which is just a transient state. And okay, and here we start editing the delay caused by the interference from IRQs. We say that IRQs are interference because they behave like if they had a priority higher than all the threads on Linux, right? We can cause a block to the IRQs because we can disable IRQs and make them to delay, but once they are allowed to run, they cause interference. Okay, as at the end of the scheduler, we will return with interrupts enabled. Even if these all were interrupts disabled, all the interrupts will be served here. So we need to account how much interrupts we could have in the entire window of time from the first condition to cause the reschedule up to the point in which we return the control to the new highest priority thread. With that explained right here, I'm not showing all the details of the argumentation that we have in the paper. Go there, it's not that hard after seeing the explanation. And here we say that the latency, the theorem says that the latency is bound by the maximum value between the scheduled tail delay and the preemption or IRQ disabled, whichever one of these is higher, we will pick the highest one, the maximum one. Then that transient state, then the time to call the -- schedule function inside the preempted disabled that it runs. Plus the function that returns me how much interference I can have during the latency from NMIs, and the function that say how much interference I can have from IRQs inside that L. And as you can see, the L is in the both side of the formula. And that's common in the real-time theory. It's based on the real response time analysis theory. In which when we have these two cases, let's say that I have a maximum here of 5, then I add NMI, it goes to 6, then I have NMI, it goes to 7. Then I recompute this with 7, right? And then if we're okay, this doesn't increase anymore after 7, then we have the stable latency, stable L, and that's the L. Okay, looking back here with the timeline, it's easier to understand it. So is the maximum between this delay that will cause the behavior here, or this delay that will cause the behavior here, plus the interference. True? No. Okay, Daniel, but so far you haven't talked about these functions that define the interference from IRQs and NMIs, right? What are you hiding here? Yeah, last year at Plumbers we discussed this. I gave some brief ideas of what I was talking, and actually these diagrams that I'm using today were designed for last year's, and we used them at the paper. So the point is that there is no best way to characterize how much interrupts you can have on a system. And it will depend on the design of your own system, right? You can have a CPU isolated, or you can have the CPU handling your mouse, and you can do like this and cause a lot of burst of interrupts. So there's no single way to define the characterization of IRQ, or there's no single best way. So instead of trying to convince about a way that could be pessimist, that could be optimist, we did the analysis considering well-known characterizations for the IRQs in the experiment. And that's why we put the IRQs in the formula. This will get easier when we reach the tuning part. I'll explain, and we will analyze some latency analysis using these different curves. Okay, episode 2, getting practical. So 2 years ago, I explained the model, but it was a little bit hard to process all those events in user space. And then last year, I came with the idea of doing runtime verification inside the kernel, and showing that that idea of processing events in kernel was good enough to be used in production, and that allows us to reach here with the tooling part of this paper. So, okay, it's nice to have a formula. It's cool. I can show to my friends in the academia, and they would say, "Woo, I like it." But when you go to the practice, when I came to this side of the fence, if I don't show a tool that can actually pop me out some numbers, it will be just a piece of paper, right? So, and here we get back to the Linux side of the fence. So I created a tool based on the latest bound, explained it there. And the latest bound was based in the model that I presented 2 years ago. And the model caused a lot of data, hundreds of megabytes per CPU per second, and that would not be practical, right, in our user space. So the challenge here was to minimize the runtime overhead and to make it work somehow out of the box, the tool. And here's the structure of the tool that we created to do the latest measurements. Actually, this structure is already updated structure. It's already different from the paper we published. This will probably be the version that we'll send on an extension of that paper. And it has these 4, let's say, components. It's 2 components, one in kernel and one in user space. And this user space has 3 subcomponents. And we will get more details. Yeah. So in the kernel side, we did an in-kernel trace parser in which I hook to the kernel events that I need to look at. And they are mostly the preempt and RQ disable, which happen on a very huge frequency on the preempt RT. And also in the RQs that start and goes away, and the scheduler. As these events happen too often, I cannot export out this data to user space. I need to do the filter here. And that's what these RTSL events do. Instead of exporting out the trace, it exports the value for the variables that I use in the equation. So I export the value for POID, for the PST, here, already processed. Trying to lower down the number of events to put for user space or to be consumed by the BPF. And so the point is that this in-kernel filter, it requires some change in the kernel. The major, let's say, major thing here is that I depend on the parameter RQ trace points that can cause some overhead. And so this tool won't work for a kernel compiled to have support for this. It will not run on any kernel. It needs these trace points, enable the completion time, but life finds a way. We can always improve that. And it also adds some annotation to the preemptive disable to notify when the preemptive disable was called actually to run the scheduler. But these are non-functional chains. All these things here are non-functional chains. I'm not changing the behavior to make the tool to work. I'm just editing annotations to get more information from the trace points, but no functional chains. That it would not make sense to change the kernel to fit the tooling, right? So no functional chains. Then I have the user space side. I have the record, the RTSL, which is a command line. Is a tool. It was made in Python because Python is easy to make proof of concepts, right? So when trying to measure the latency using this idea, the first thing that I do is do an RTSL record. It will enable these events. It will hook to these events, and will trace the events that I want, and save it. The RTSL here is a Python script that dispatches either perf or trace command and saves the trace data. It will get easier when I show the demo, right? Just explaining here the both. Then, after doing the record, I can do the parse of this trace data and the analysis of the data that shows me what would be my scheduling latency on that system. So I get the trace file, And I parse it in parallel per CPU. Like for each CPU, I dispatch one perf or one trace command, and I convert the trace data into a per CPU database. And the reason for that is because for me to do the analysis of the interference from IRQs, I need to go back and forth in the data. I analyze all the IRQs, find a worst case, then using this worst case as parameter, is there any worst case that could be even worse? Because now we turned the window a little bit higher, then parse all the IRQs. So I could do this in memory. In the first person, it was in memory, but one day of trace generates like gigabytes of data, so it was not practical. That's why I used the database as a backend. Then I dispatch one thread per CPU here and do the analysis of the latency per CPU. And then the analysis, I print a analysis in a text format and also plot some charts. Okay, here I was continuing the discussion and explaining this. Here's one example of the output of the tool. I will show a demo soon. So, but for example here, I get the maximum values for those thread variables, the maximum observed value. And I said, okay, if I consider no interrupts, my latency would be 42 microseconds. The time here is in nanoseconds. But at the same time, cyclic test running on that CPU, at the same time frame in parallel, it just found 47. And the reason for that is that cyclic tests just get when it set the timer and it measures. But we have no evidence that we found the worst conditions of this case here, the worst condition of scheduling delay, the worst conditions of preemption or IRQ disabled on that set. And here, instead of getting like just the combination of the worst scheduling or the worst IRQ disabled that take together, I got those separated. So I've noticed these preemption or IRQ disabled in the system, and I noticed this PSD, and as they are independent variables, I can sum them up. And there is the background on real-time theory that shows that this is possible, right? And then, okay, considering no interrupts, I can also find already some latencies that are higher than cyclic test. But then I can use some well-known IRQ characterizations to add also the delay caused by IRQs. And one common characterization from the real-time theory are the periodic tests, like that we use the minimal inter-arrival time between two instances of the same IRQ or tests, but here IRQ are tests, and the worst case execution time of that IRQ. And this is prone to be pessimistic, and we discussed this last year. And in that, it is because very often the minimum arrival time between two instances of an IRQ is even lower than the maximum execution time of those IRQs. So yeah, sporadic is too pessimistic. No interrupt is too optimistic. And here we have the sliding window, which is the one I prefer most, that gets this. It gets the latency, the block latency. And then for each IRQ, it scans all the vectors and say, okay, for these 42 microseconds, my IRQ 33 could increase it in 16 microseconds. Then I get the IRQ 35, and I see that it could put up plus 40 microseconds on top of this window, and so on. Then I reach a latency, right, using these parameters. But then I need to go back to our IRQs to say, okay, considering this time window, could I fit any more interrupts from the 33 vector, and so on. And here we found a case in which the timer could put yet more interrupts in this time window. And we reach a stable value of 98 microseconds. And then, based on that, I can also plot some charts comparing. And I will do the experiments explaining later, but here are on a system, in the same system, running with the same conditions. Yes, I probably say 47 when I have to say 27 still. So here I compared the system with 12 CPUs here. These were the values found by cyclic test. And at the same time frame, the cyclic test could not catch these cases in which I'm not even considering interrupts that got worse. Then if I just added one interrupt, the worst of them all, I could even have higher latencies. And getting one of each interrupt vector even higher using the slider window and using the overly pessimistic thing. So depending on the RQ, we can estimate a different latency. But it's hard to define which one is the worst, and the users of the system should say that. But personally, I like this. So another tool that we can have here is the RTSL stats. Inside the RTSL, we have a subcommand that it monitors the value of these variables, the blocking variables, in kernel using the BPF, and I save the histograms inside the kernel. And periodically, the user space side using Python and BCC, I collect the histograms and I show these values there, like showing. I'll show it in a demo, and it will be more intuitive. So I'll show you all the demo now from the tooling work. Just a second, getting the YouTube. So here I recorded 10 minutes of the trace, and I did this yesterday. And here is the trace data. It was with ftrace. It was 176 megabytes of data in the 10 minutes. You can see it's not too much, but still considerable amount. And then I do the report, trying to make the analysis of the latency with this tool. As you see here in the top, it first does some analysis in the trace, and then I dispatch the trace or perf in parallel, converting the trace into a SQL file. And you see they use all the CPU because they're running in parallel. And then when it's Python, it's doing the analysis. You see the analysis is actually fast. And here we can see, I'll show some values, like I have the header that I explain what are these values. And then I show the latest analysis of CPU0 with the actual values from the system running. This is not a very optimized system, so it will be large. And I show the interrupts, how much interrupt I could have. And these are the latest analysis. I will show later in the experiments some typical values. So if I run it, the report again, I will not parse again the traces, so the analysis will be faster. So the vast majority of the time, I'm just converting trace into the database. The database is not that slow. And here are the database files generated. And let me go pause here. And it's good to have these files in SQL databases because later, other researchers that are not familiar with Linux, they could use this data to do a more sophisticated analysis on IRQ, for example. And it's straightforward to use Python. And okay, Steve, I'll put later these slides. I forgot to put the slides as download. Anyway, these are all available already on the site, but I can put it. So here are these .rtsl files are SQL3 database. And now I use the stats to show the values that are actually happening on my system for the POID variable. And here I'm using the BCC to collect these variables and show the histograms. And I can also plot things with matplotlib. That's why it's good to work with Python user. And also, I can find where in the system those like larger POID numbers happen using perf, for example. And I can also extend RTSL to make this using the BPF. So here, for example, I can show the trace that I collected in which the preemption RQ disable took more than 20 microseconds. And that's good for debugging the system, right? And yeah, that's it. Okay, thanks. Thanks for posting the link. And okay, stop. Going fast now. I run some kind of experiment showing how pessimist we are using this using this technique. And here's a single core. This is the cyclic test, and this is the latency only considering block and considering some arrival curves. And we can see that, okay, I'm getting pessimist for some arrival curves, but still the values are not bad. Even getting the worst conditions that we observed during a trace, even put all the worst cases all together, unless we use like a very pessimistic arrival curve for RQs, the values for the RQ, the parameter latency, are still good. They are still in the 100 and something here for the single core case. And even if I go for a case with multiple CPUs, now the experiments are running background workload to try to find bad cases. You see, with the sliding window, which is the most practical in my opinion, we are still getting like 250 microseconds latency. Or here, less than 350 microsecond latency, even with pessimism. And even with the overhead added by this tool. So yeah, the parameter T does very well, even when we do some pessimistic analysis, with all the pessimism that we get from the theoretical analysis. And that's good, that's impressive. So some remarks here. The parameter T model is deterministic, and we have shown this. We don't need to put this around the determinism. Oh, okay.
5 minutes.
High five.
5
so
minutes.
the parameter T, it has a parameter model that is deterministic, and we show with the model. The approach presented for this paper is not the end of the line. Instead, it is the beginning of a more sophisticated analysis that can be done by the researchers in a researcher level. And even though the RTSL finds higher latency, it's still not large enough to make Linux not usable for the use case that we have. Instead, it justifies the usage of parameter T in even more critical scenarios, because now we have a more strong evidence of the latency. The RTSL is practical. Okay, we need to enable some things at completion time, but still it's practical because it doesn't add enough overhead to turn it unpractical. RTSL versus cyclic tests, they are not rival. They help the same people, but the RTSL is a more specific tool. It covers worst cases. But it depends on kernel features, and it does a worst case scenario. It's not shown yet, like a minimal and an average case. Cyclic test has another purpose and capture other things. And curiosity, when I run RTSL together with cyclic test, it's adding a 4-ish microseconds overhead over cyclic test. So as you can see, the RTSL is not adding too much overhead. Instead, it's impressive to see just 4 microseconds, given the amount of trace that we need to parse. The code is on my GitHub. I was planning to send it today. It's based on 5.6. That was the latest RT kernel up to earlier this week. Oh yeah, no, I said that. I said here that the cyclic test could run on a potato that runs Linux, in the sense that if a Linux runs on a potato, you can run cyclic test. But that's not the RTSL case, because it needs the parameter T with some tweaks. So I was planning to send today the kernel patches, but there is a newer RT version. Should I send it with 5.6 or should I update it 5.6? Should I send it with 5.6 or update 6 to 5.9? And yeah, that's it. I'm open for questioning. And I made in time. Don't be shy. No questions? That's bad.
If pre-emit RT disabled, U2 keys is still could be used in or analyze the system latency.
I'm sorry, I didn't get the question. Could you?
I mean, if the pre-emit preempt RT disabled, the macro of the preempt RT disabled, U2 keys could still analyze the system latency.
If I don't have like the.
Yeah, if we don't have the pre-emit RT, RT TL LK is.
You mean if I don't have the trace points enabled? You mean if I could do the analysis?
Yeah. I mean, we just utilize the current trace point but we didn't enable the pre-emit RT. So if the two keys you have mentioned could be utilized
Let me try to state the question and see if I get the right thing. Would your analysis tools work on a normal non-RT kernel? Is that what you're asking?
Yeah. That's it.
Okay.
No, because it's based on the precise specification of the model for the preempt RT. For us to extend it for the preempt but not RT, I need to analyze the software queue, how the software queue behaves on the preemptive but not RT. If they still have a higher priority than threads, then I would have to edit it. The bound, that delay caused by software queues. It would not be that hard. For the non-preemptive kernel, then we need a different analysis because the preemption model is different. And this is restricted to the preemptive mode. That's why it's very specific thing. You're mute, Clark. Soft mute.
Oh, actually, I just want to jump in real quick. I kind of missed a little bit because my microphone went dead. I had to hang up and so. But anyway, one thing about if you do it without preempt RT, you have unbounded latency. So the worst case scenario is infinite.
Yeah.
So you can run it and see what the system would be, but the analysis should probably come up with an infinite scenario.
Well, is that really true? I mean, that depends on your restrictions on interrupts and other things, right?
No, actually, I could actually set up a system where I will, if I were not to use PI futexes and such or whatever. I mean, if I were to set up a system where inside the kernel, I think I could probably pin things up so I could preempt something. I did this before. I was able to hang the highest priority tasks that shared a resource.
Deadlock it or live lock it?
Well, no, it wasn't deadlocked. What happened was
kind of a live lock.
No, it was the simple priority inversion. I had three tasks: high, low, middle, all sharing the same resource. Had it so that the high would block on the low, and then the middle one would run, never letting the low one release the lock, and the high one would stay there forever.
Okay,
that's the PI test that's in RT tests.
Well, we test that. You can lock that up if you don't use PI futexes in the real case, you can lock up a normal RT kernel. I'm saying I did this in the kernel. I had the kernel was able to trigger this.
Interesting.
So we should probably let Clark ask his question, and we're kind of at the end of time. Not that there's anything afterwards. Go ahead.
I guess I was just observing that since the current model is kind of built around preempt RT, doesn't that imply that anytime we change that scheduler parameter, you have to generate a new model?
No, the analysis is all done. It's a model. It's a scheduler agnostic. I'm not using any abstraction that is for one specific scheduler.
I guess what I'm saying though is, if you switch from using a preempt RT kernel to say just a plain preempt kernel or voluntary preempt, that's what I meant.
That needs another analysis. Yeah. I need to create another model that represents that preemption model, and then I should do the analysis on that preemption model.
Right.
It's very specific for the preempt RT.
I have a question. I'm curious. Would your model actually catch the priority inversion, or is it just assume that there's priority inheritance?
The model didn't model the status of the locking. We can create a model for this, but the model is not capturing.
Oh, that's right. So actually, we could have longer, a high priority pass. That's just a schedule wake up. So basically, assuming that the guy that's not holding any resources is just waking up, that's what you're basically modeling.
Yeah.
So that might work on a non-preempt kernel.
No, the point is the software queues. Is the software queues behaving the same way that in the preempt RT? Are they like on the thread context? Yeah, that's the difference. Then we need to add the abstraction of the software queue. If software queue were on threads, it would work, probably.
Okay, we're out of time, but there's nothing after us. People that need to go to another talk, go to another talk. I have to go somewhere else, but I don't see any reason not to continue the conversation right here. But I want to take a time out to thank Daniel and thank everybody for the questions and everything. And, great start to the last day of Plumbers. Thank you very much.
Thanks, Daniel. I'm off to CTF, so talk to you guys later.
Okay. Yeah.
I have a question. About because in most of the charts we see cyclic test as a lower latency than most of the models. I'm curious if there is a way to tune the model so it shows the same data as the one you get from the experiment with cyclic test.
Well, I could ignore I could just capture the case in which the wakes up. That instead regrescad is actually being heated because of cyclic test trying to run. But that would not make much sense from the real-time scheduling theory.
Mm-hmm. Because I'm just curious if it's because cyclic test is so active and it makes a difference in the latency compared to the other models.
All here are running at the same time. I'm running in parallel.
Mm-hmm.
I expect a test which is I'm tracing to get these values while cyclic test is running. So I'm capturing the same scenario here. I'm analyzing the same system at the same time with same workload.
Thanks.
And yeah, it's getting lower because it doesn't capture the worst scenarios. And actually, it doesn't mean here that the worst scenarios took place altogether, right? The formula allows us to postulate that this could be the latency, the higher latency, but it actually might not have happened in the sequence.
Thanks.
Question, should I send the patch set based on 5.6 as it is now, or should I update for 5.9 and send it next week? What do you think, Clark?
I say we just set it up for the next one. It was a good talk though, Daniel.
Oh,
I
thank
learned
you.
something.
Yeah, it's a little bit heavy. Though.
Yeah, that's not that bad. Okay. Well, I'm going to have to go to another meeting. So anyway, thank you, sir.
Thank you all. Thank you, sir. And thank you all. I'll have a beer because I'm tired. And it's late here. It's time to go home. I'm actually home. Thanks, Yuri.
Congrats, Daniel.
Thanks, Luis.
You are currently the only person in this conference.